The topic today is how we know what the bonding in solids is like, or what the geometry and what the structure within a solid might be. The answer, in a sense, in a great sense, comes from this funky looking machine, very complicated, that shoots some electromagnetic radiation at this sample in the middle here. And there's a computer analyzer over here that watches how it bounces off. It's a very, very, like I said, um, computationally intensive process, and it's called an X-ray diffractometer. We shoot X-rays at the sample and watch how they bounce off of it. It was originally back in the 1950s how we learned what the structure of DNA was, a double helix kind of a thing. X-ray diffractometer. So in solids, we find several possibilities. Molecular solids are molecules that may be a solid at room temperature or may just be cold and freeze into a solid. This first one's a carbon dioxide. It's not a solid at room temperature, but indeed it freezes into a nice crystalline structure in the form of dry ice. Or benzene, if you were to freeze benzene, which isn't too hard actually, it freezes at a reasonable temperature. Benzene is usually a liquid. There are enough interparticle forces in C6H6 to hold it in a liquid as opposed to a gas, and it's also pretty easy to freeze. But cool structure of C6H6 at the corners, and looks like one at the face, and one down here, and one here, and one here, and one here, and one here. It's like a face-centered kind of a structure, if you've watched the video on unit cells. Another possibility is a small group of solids we call covalent network solids. There's such a small group, it's worth memorizing that diamonds slash graphite and glass are pretty much the only covalent network solids. And by that I mean they're covalently bonded together. The carbon atoms in diamond and carbon atoms in graphite and the silicon dioxides in sand, like this, or glass, or quartzite, are bound together in big, huge, gigantic structures, a big network of atoms that form a solid. What makes diamond different than pencil lead? Oh yeah, when I write with pencil lead, it sloughs off. This layer sloughs off, this layer sloughs off, this layer sloughs off onto the pencil. But the diamonds are pretty much bound in 3 dimensions and really, really, really rigid, really strong. Honestly, I don't know why I included this slide, just because of all the variation in the solids. But solids do stick together in nice repeating crystals, and that's why the X-ray diffractometer is perfect for discerning the structure of that crystal. Yeah. Here's again the benzene and the diamonds and the graphite and the silicon dioxide, sand or glass. I'm going to skip that one for now. It's interesting, but another small possibility is that the solid is an atomic solid. This only happens with the noble gases, and if you can liquefy and subsequently freeze a noble gas into a solid, all you have is atom, 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 atom. Looks like a face-centered cubic structure, but these atoms forming an atomic solid are all there is to that unit cell. Kind of weird, but remember that if you can. Ionic solids, we've already talked about them in a way in the chapter on ionic bonding, where the positive and negative stick together. Or if I knew something about the geometry of the cell, maybe I could count how many units of cesium and how many units of chlorine in this unit cell. Looks like one cesium because there's 1/8 of 8 and one in the very smack dab center. So in a sense, the diversity and description goes on, but we've sort of seen ionic solids a bit. Metallic solids are what happens in a metal, of course. It's one thing that makes metals so strong. We imagine actually that the metal atom is stuck in a lattice, but the valence electrons on the metal are kind of free to go wherever they want, and they're attracted to all the dozens of neighbors in the same vicinity, and so the positive nuclei of the metal atom attracts the negative electrons of its neighbors, and that's one thing that makes metals very malleable or highly conductive electrically speaking too. Um, Molecular solid, molecular solid, these are all molecular solids. There's quite a variation in the melting temperature of molecular solids, depending on what interparticle forces you're talking about. Hydrogen bonding with NH3, dipole-dipole and hydrogen bonding, dipole-dipole and hydrogen bonding for ammonia and water, dispersion forces for these. So they tend to, yeah, I'm not going to touch that one. I'll just say interesting. Same story here with melting points. Well, for the covalent network solids, silicon dioxide and diamonds and graphite, they melt very, very hot. So covalent network solids have large interparticle forces in that sense because they're, in a sense, covalently bonded. Here I have some salts. There's quite a variation in the salt melting temperatures, but still salts are hard to melt, so the temperatures are hot, even hotter than metals. No, not always. Look at copper and iron. Copper? No. Oh, yeah, that's right. I was thinking about zinc. Yeah, copper and iron and tungsten hard to melt. Last slide and the answer. Which organizes these in the proper molecular solid, ionic solid, atomic solid, covalent network solid, or metallic solid? More anticipation music and pause the video if you like. I think the answer is something like there aren't very many atomic solids, only the noble gases. There are also aren't very many covalent network solids, only diamonds and graphite and sand. Is cesium a metal? Mm-hmm. Is calcium chloride an ionic substance? Mm-hmm. Is CH4 methane, if you could freeze it into a solid and have a molecular solid, is that a molecule? Mm-hmm. Choice B. Thanks for watching, guys. I don't know how confusing this is, but I remember the first time I heard about it, actually I was confused. I'm like, this is too much information. Anyway, sleep on it, ask questions, see you in class or discussion. Thanks.